So, let's see. Last time, one thing we did was go over the homework, and I discovered I had done the game incorrectly. So, here is my solution to the game. You can take a look at it, see what you think. I don't think I'll really spend time with it. Armando did it graphically. Let's see. I have it, I think it's clear there. I kind of went about it two ways, and they came up with the same solution. One way is the brute force way, and that's just to write all the combinations down. And what I did then was I underlined, well, I let 1 be the smallest number, 2 be the next smallest, 3, and so forth. 4 is the biggest. So whatever's true for 1, 2, 3, and 4 is going to be true for any set of 4 different integers, and obviously the biggest is 4. And I underlined the one that the strategy, the best strategy that we described, would lead you to choose. So whenever that choice is a 4, your choice wins, and whenever it's not a 4, your choice loses. And so then you can simply count up. There I counted up the probability that choice of 1, that's P superscript 1, is picked is 0. The probability that 2 is picked is 12/24, because there are 24 combinations, and so on. And the next column says the probability that 2 is picked and that it's a winning choice is 6. You just count them up, and so on. And so the total probability of making that the strategy leads you to pick a winner is 11/24, so on. Which I believe is what I came up with my wrong method. But the individual probabilities were not right. Some of them were right, some were wrong. And then below that is a way to the same result with logic. And I'm just going to read a couple of them so you know what it means, and then you can stare at them if you care later. P2 is 1/2 because the probability that N2 is greater than N1 is 1/2. So that's half the time you will pick 2. Now the probability that you'll pick 2 and that it's a winner, I say, is 1/4, and that's because the probability that N2 is 4, the biggest number is 1/4, and the probability that you will pick N2, given that N2 is a 4, or the biggest number, is also 1. Is 1, so then 1 times a 4th is a 4th. And then you probability of losing on picking 2 is then the difference. I'll just read the next one then. Probability of picking 3 is a 6th because the probability that N2 is less than both N1 and N3 is a 1/3, and the probability that N3 is greater than N1 is a 1/2, and these conditions are independent, etc. So you can look through it if you have a little spare time and see if you agree. But with the logic, I got the same answers as with the enumeration. So it turns out if you think in terms of logic, you have to think of whether 2 conditions are independent or dependent. So then, I think that's all I wanted to say about that. So back to this chapter. How's the reading? How's it? Understandable? Not understandable? You didn't read? Uh-oh. Anybody else? Is it understandable or? Well, let's review where we were. What we're doing in this chapter is making a connection between the partition function for a system in terms of something simpler, namely the partition function for particular molecules or particles. And what we saw last time was that we can write the canonical partition function as where little q, which depends only on v and t, where little q is a single particle or single molecule partition function, and so it's a sum over the exponential of minus beta times the energy of a particular state of a single particle. So it's a single particle state, not the state for a system. Now this is based on a few assumptions. One assumption is that there's no interaction between the particles. If there's an interaction between the particles, then this is not strictly true. And second, notice the factor of n prime. That's there because these particles cannot be distinguished one from another. And so what you find is without the factor of m prime, you've vastly overcounted the number of states available to you. Each distribution of particles along energy levels can be realized in n prime different ways, but you can't distinguish between the particles. And so that's where that factor came from. That was one assumption. So the n prime comes from two assumptions. One, we're correcting for indistinguishability. Of particles. And the other assumption we made is that the temperature is high. Or more precisely what we assumed is that the population of any particular single particle energy level is 0 or 1, no more than 1. I shouldn't say energy level, I should say state. All single particle states are at most singly populated or singly occupied. So those assumptions were behind this. And this came from the idea that at high enough temperature, there are so many states available, many more states available, energetically available, than there are particles. So the probability that any particular state is even doubly occupied is negligible. Okay. So that underlies this. And this expression for the canonical partition function in terms of the single molecule partition function is called Boltzmann statistics, really. We call this Boltzmann statistics. Now what I want to do, and we know that if we know capital Q, then we can determine all the thermodynamic functions for a macroscopic system. And of course, to calculate Q directly, big Q, the canonical partition function directly, we have to calculate the energy levels of the system. How are you going to do that? You've got a mole of molecules. But this relationship says, hey, if we can calculate the energy levels for particular particles, we can construct the single molecule partition function, and from that, the canonical partition function for the system, and from that, all thermodynamic properties. So Gaussian will tell you the Gibbs free energy per mole of your stuff. It's based on thinking of your stuff as an ideal gas. So that's great. Now what I want to do today is generalize this where we no longer make this second assumption, and where we realize our wave function has particular symmetry properties that we need to take into account. What do I mean by that? If you think back to computational chemistry or quantum mechanics, when you're thinking about something, even some atom bigger than hydrogen, you have several electrons. And one principle you have is that, let's say, butt. This is the big butt right here. But for electrons, a multi-electron system, we know that if we switch the position of electrons 1 and 2, so these numbers simply label electrons 1 and 2, then the wave function has to change sign. We say the wave function is antisymmetric with respect to the interchange of any two electrons. The thing is that macroscopic, that electrons are not distinguishable, and so our intuition starts failing when we get this small. I mean, if we think in terms of 8 balls, and all 8 balls are black, but if you have 2 8 balls on a table, when you look really closely, you can probably find a scratch in one that's not in the other. You can distinguish them. Or, even if you can't distinguish one from the other by looking at it, you can think, hey, I know if I had a camera here, and I knew at one point in time where each one was, you can imagine having a camera in that room. You can always figure out which one's which by how they move, right? That kind of thinking fails when you get to the microscopic. You can't distinguish one electron from another. It's not like one's green, one's red. And so any description of the system that is based on distinguishing, being able to tell which is number 1 and which is number 2 it's bogus. Okay. So all we can say is that if you do interchange them, this wave function has to change sign. And in quantum chemistry, of course, we do this by using Slater determinants for our basis functions. So any particle that for which the wave function obeys this antisymmetry property, or has this antisymmetry property, we call a fermion. WRT is with respect to and the alternative, of course, is a boson. Photon's a boson. For which the wave function does not change sign on interchange. That's a boson. So what we want to do is derive, come up with expressions for the partition function, the system partition function for the system in terms of either of these two possibilities. And we want to relax this restriction of high temperature only. So that's what we're going to do. It's done in the book. After we've done that, we'll go to high temperature. The book does it for both fermions and bosons. I'm just going to take one, for example. We'll see in particular how at high temperature, the expression for the partition function for a fermion becomes identical with that for Boltzmann statistics. We won't look at the partition function exactly, but we'll look at something else, probability. Okay. So we'll see that really we don't have to worry about this distinction at normal temperatures for us. Only if you get really, really cold. I passed out there's a table in the book. I passed out a sheet last time. Only then do you have to do it. So, we have to begin then simply. The hard part is the beginning, making a mental leap, and then after that it's all easy. Okay. Okay. So we're going to want to think about the energy of a state of the system. So I'm using J to label states of the system. In terms of energies of particular particles or molecules. So in this case, the K labels the state of the single particle. So this is the energy of single molecule state K. And this, of course, is system state J. And N sub K then is the number of particles or molecules in this single molecule state K. Think of those as bins. I'm saying molecule, you might want to think particle. The small thing is all that matters. Now there's a constraint, of course. If we're thinking a canonical system, at least, if we're thinking in terms of the canonical system, which we have thus far, then the constraint is that if you sum over all the n sub k, you have the number of particles in the system. Okay, that's a constraint. So now we can write down Q, of course, which is for fixed n, v, and t. Which is just that sum over the exponential and minus beta times the state of the energy. I'm sorry, the state of the system, the different states J. But we can write this in more detail. Maybe it's easier to write it this way. So this I've simply rewritten at E sub I in terms of the epsilons i's. And this is a j, E sub j, these are epsilons of i's. I'm not going to go and add a superscript j, okay, it just gets too busy, but you can think that in your head if you want. Now, the book uses this notation to recognize this is a sum over all the n sub i's, but there's a constraint. And that constraint is this constraint. You can't just sum over every value of n sub 1 and every value of n sub 2 at this point, right? There are only particular ones that are allowed because of this constraint. So that's what we have to work with. And it turns out what we want to do simply is evaluate this sum and simplify it in some way. It turns out that it's hard to think about this. It's easier to think and evaluate this sum actually if you go to a different ensemble. And remember, all the ensembles are equivalent. Once you get big enough, you're macroscopic, they're all equivalent. It turns out that it is easier to think in terms of the grand canonical partition function, even though it looks so funny when you write it as a Greek symbol, where instead of n being held constant, mu is constant. Remember, mu is the chemical potential, gamma was our Lagrange multiplier, and gamma we saw was equal to mu over kt, or just kn mu. Right, going back. Or actually, we're going to use another, and remember we defined gamma as e to the, so we defined lambda as e to the gamma, or e to the beta mu. Just to remind you, we'll be using that. So then, the grand canonical partition function is the sum over n of e to the beta mu n times q. Remember that? So, we can rewrite it this way. And for convenience, notice that I can replace this n if you would want with the sum over the little n's of i's. They simply sum to n. And I can rewrite this as left off something. It's the product of all of these. Because the exponential of the sum is the product of the exponentials. Okay. So that's straightforward. And the mental leap that we have to make, and that is not probably obvious, I think the book says, and this takes some thought. Those are the words in the book. This, in fact, equals or if you like, you can write that this way. So what we've basically done is interchange the product and the summations, but you're left with only one summation. And that's a real important step to make, and I don't know if it's obvious to you or not. that it's legitimate. As the book said, it takes some thought. I saw a head shaking, so it's not real obvious, or it's... Well, the way I think about it is this. Notice that we're summing over all possible values of capital N. We could have 0 particles, 1 particle, 2 particles, 20, 10,000 particles, all possible values of N. And for each of those values of N, we've got this product over the individual energy states accessible. The individual states accessible for a single particle. Now, let's think about that. So we know we can label the single particle states as, if you like, state 0, state 1, state 2, state 3, state 4, right? So any particular state of the system will be labeled by the number of particles in state 1 times the number of particles in state 1 times the number of particles in state 2 times the number of particles in state 3. Right. You can distinguish particles in state 1 and state 3, but you can't distinguish the various particles that are in state 1. Okay, but each of these vectors is a different one. Okay. So, and now it's the different values of these n's that we're having to take this sum over, right? Then we take the product over all the i's. So, the very first one of these is N0. Suppose that these other n's have some particular, you're going to think about some particular set of values for them. Maybe N1 is equal to 1, N2 is equal to 7, N3 is equal to 2, and so on. This is only one of, if we ignore N0 for the time being, this is only one of many possible combinations of the N1, N2, N3, and so on. One of many, many, many. But let's suppose we're just going to think about this one set of values of N1, N2, and so on. Okay. Now think about N0. N0 can be 0, N0 can be 1, N0 can be 2, it can be 3. Every possible value of N0 can be combined with the particular set of N1, N2, and N3. And each, once you combine it, each one of those is a particular state of the system. And that's one state of the system. So what we find then is we can combine N0 with one time with each of all of the combinations of N1, N2, and N3. Okay. The reason we can do that is because we're summing over all the n's. Okay. That means that we can, from this, we can take the N0 thing out in front. Because N0 is just one of these terms in the sum. I'm sorry, we can factor out this, this stuff for N0 from every term in the sum. Okay. So this becomes times the rest. Except now we've already dealt with N0, so we're not including the N0, it's out in front. Now, there's nothing special about N0. We could just as well have talked about N1 or N2 or N3. So in fact, we can bring the corresponding sum for any one of the i's out in front. And that's what I've done here. Okay. So we get to here. So, that's it. That makes sense, wonderful. See if it makes sense later in the afternoon. If it doesn't make sense, ponder it some more. It's one of these things, beyond this I can't take you any farther. It's just this mental leap your brain has to make. Okay. But this is now where we have to take off from. Erase all this. Rewrite this. So what we have then is that the grand canonical partition function, and by the way, we're talking about Fermi-Dirac statistics. Oh no, we've made no distinction yet. Forget that. Okay. Grand partition function. We have not yet distinguished between fermions and bosons. What we've said so far is true for both. I mean, this is really a very nice thing. We no longer have this sum where we have a constraint. This is now there's an unconstrained sum and an unconstrained product. Okay, so this was the beauty of going to the grand canonical partition function. Okay. In the canonical partition function, we had this constraint, and so it wasn't quite clear how to use the equations. So I can erase this. Okay, that's really about it. Now let's think in terms of fermions and then in terms of bosons. So for fermions, and for fermions one speaks in terms of Fermi-Dirac statistics, these people who worked out that. Now for Fermi-Dirac statistics, we noticed that each state can be at most singly occupied. You can't have two fermions occupying the same state, because if you did, you'd have psi of 1, 1, 3, and when you interchanged the two particles, you couldn't distinguish the resultant wave function from the starting wave function. It wouldn't change sign. But for fermions, the wave function has to change sign. So you can only have a population of the single particle states of 0 or of 1. You can't have a population of 2. So this product then FD for Fermi-Dirac. The sum just goes from 0 to 1. If n sub I is 0, we just get a 1. And if n sub I is 1, we get That's the grand canonical partition function for a fermion. And now you can do anything with this that you could do, any manipulation of the grand canonical partition function that you got from the previous chapter. From it, you can get the pressure volume product. You can get the average energy for the thermodynamic energy. You can determine the Helmholtz energy, the Gibbs energy, anything you want to. Okay, but if this is a fermion, you need to use this instead of this in general. I will show later that you'll get this equivalently at high enough temperature, but not at low temperature. So that's that. What about bosons? We speak about, again, the people who work this out, Bose-Einstein statistics. So these are really great terms for cocktail parties, things like you want to impress somebody. You just talk about Bose-Einstein statistics and Fermi-Dirac statistics, throwing a Boltzmann here, Boltzmann there. They get very impressed, They really entered high geekdom, So I'll use BE for Bose-Einstein. Now for Bose-Einstein, we have no restriction in the populations of the single particle energy levels. It can be anything. So it kind of looks like we're left with that. But we can be clever algebraically. And remember, if x is between 0 and 1, then 1 plus x squared plus x cubed plus etc. is 1 over 1 minus x. One of these series you've seen before. Or you can go home and you can write that as a Taylor series or something. You can see that's true. So that's cool. We can probably rewrite this. Now you have to convince yourself that this thing is less than 1. Okay. I think it's obvious that that part's less than 1, right? It's positive it's less than 1. And this lambda also, it's maybe not so easy to see, but you can convince yourself. Remember we thought of lambda as an absolute activity? And just giving you a way to get there in your mind, we think of activities in the limit of something being very, very dilute as being like a concentration. So this is less than mole fraction. So this is something that's less than 1. So consequently, this becomes write it this way. That's it. Two pretty simple expressions. In fact, you often see them combined this way. Where the top symbol or the top sign corresponds to the top subscript here. So it's plus for Fermi-Dirac, and these are both minus for Bose-Einstein. It's easy to remember that way. Okay. So that's like the most important result from this class is that we now have an expression for the grand canonical partition function for Fermi-Dirac, for fermions or for bosons at any temperature. Okay. So that's important. The last thing I want to show you is that statistically, when temperature gets high enough, the results that you get for any thermodynamic function using Fermi-Dirac or Boltzmann-Einstein expressions for the partition function turn out to be the same as you would get using the Boltzmann expression for the partition function. Okay, that's grand canonical. This is canonical. But remember, in terms of either partition function, you can determine all the thermodynamic functions. So I want to show you that in the limit of high temperature, you're going to get the same thing with that as you'll get with that. Okay. So let's begin by thinking about this one. I'm not going to say that the partition function itself is going to look the same. I'm going to show that anything you get from the partition function is going to be the same if you go to high temperature. So, yeah. So let's begin with this one, now that I've erased it. And let's talk about the energy, why not? So this is the thermodynamic energy, which is right? We've seen that before. So this becomes so that's what we have to evaluate, and I think you can see it's simple. Of course, the log of the ratio will become the difference of the logs